So let us derive the energy associated with each degrees of freedom, or let's say the law of equipartition of energy. If you consider a monoatomic molecule such as helium, argon, etc., in three-dimensional space, it, suppose we have a three-dimensional space. Three-dimensional space has three axes, that is x, y, and z axis. So any molecule can move. Suppose this monoatomic molecule, let's say argon, can move in the x direction, it can move in the y direction, or in the z direction. So this motion is called a translation. So it can translate in any of the three or all the three axes. So let we say degrees of freedom f equal to 3. Suppose it is moving in the x direction with a velocity vx, then we have the energy associated with it will be half m vx square, right? Or if the particle or if the gas moves in the y direction, let's say this as ex. If it moves in the y direction, then the energy will be half m vy square. Clear? So that's the case of monoatomic molecule. Suppose if you have a diatomic molecule, let's say oxygen O2. This oxygen, let's say, let's this is just a rough sketch of the O2. Here it is O and here another O. For this diatomic molecule, it can rotate. Okay, the rotational motion is also possible. So the energy associated with the rotational, let's say E rotational, is equal to half I omega square. This is the expression for the energy associated with rotational motion, where I represents the moment of inertia, omega the angular velocity. Suppose for any molecule, for any non-rigid molecule, if it has vibrations, this molecule can vibrate to and fro. That is, let's say if it is vibrating along the horizontal line, then the energy associated with will be it's just like the vibration of a spring. That is, energy associated will be maybe that energy will be the potential energy equal to half kx square, where k is the spring constant. Now, so these are the different energies associated with different molecules, either it be monoatomic, diatomic, etc. And if you look at all the equations of the energy, you can see that in every equation there is a term 1 by 2. Clear? For all the equation there is 1 by 2. And there is a square. This Vx is the variable in here. Here the variable is displacement x. Here the variable is displacement x. Here the variable is omega. So here, if you look at the equations, it is the square of the variables. Clear? And thirdly, as the third term, it is a constant. Here m is the constant. Here spring constant is the constant term. Here the moment of inertia is the constant term. So every energy is of the form, there is always a 1 by 2 term, then a constant term. Let's represent that constant as some mu. Then a variable square. Let's say variable as alpha square. Here mu is the constant and alpha is the variable. So every equation, let's say this as EI. So every energy equation is of the form half mu alpha square. And this is a quadratic equation, clear? Because the square, there is square for variable. So energy is in the quadratic form. Clear? Now let's erase this. Now we have to define the partition function in order to find the energy associated with each degrees of freedom. So we have EI, let's write here, energy associated is equal to half mu alpha square. Also, we have, before that, we have to define the Boltzmann's factor. Boltzmann's factor, let's say that as B suffix F, Boltzmann's factor. Boltzmann's factor is nothing but an exponential form, exponent of energy, that is E minus EI by kBT, where kB represents the Boltzmann constant and T represents the temperature. So here it will be E times, but we already know energy is in the quadratic form, that is minus 1 by 2 mu alpha square divided by kBT. Then the partition function partition function is nothing but the continuous sum of, that is minus infinity to infinity, the Boltzmann factor. Clear? The variable here is alpha, so you have to put d alpha. So this is the partition function. Let's represent that as P. So it's the sum of the Boltzmann's factor taken from minus infinity. This minus infinity to infinity, integral of minus infinity to infinity represents the sum. So this is equal to minus infinity to infinity, Bf is equal to exponent of minus 1 by 2 mu, let's write it like this, kBt times alpha square into d alpha. I'm just write this equation, but I just collected these two constants together because we have purpose for this, right? So let's write like this. Now, according to Gaussian integral, we have integral minus infinity to infinity e raised to minus a x square dx. The value of this one is equal to root of pi by a. We have a derivation for this, but in this case, in order to find the law of equipartition of energy, we don't have to go deep. So you just understand that this is a Gaussian integral and its value is pi by a. If you compare that with here a will be, before, like I said, this whole thing is a. So a is equal to, let's write mu divided by 2 kBt. You can multiply this 2 with kBt and 1 into mu is mu. So that's our a. So the value of this will be, integral of this will be root of pi divided by a. Clear? According to Gaussian integral. And if you simplify this, you will get the partition function p is equal to pi by, you can substitute the value mu by 2 kBt in place of a. So mu divided by 2 kBt. This is equal to root of this thing will go up. So you can write that 2 pi kBt divided by mu. So this is the partition function. Now, how will you find the energy associated with each degrees of freedom per molecule from this partition function? We have, let's say, energy per degree of freedom per molecule. Let's say that as, or the internal energy is equal to, we have the formula Boltzmann's constant times the temperature square, derivative with respect to temperature of log of partition function. So this is the formula for the energy associated per degree of freedom per molecule. And you know P equal to root of 2 pi kb t by mu. So this is equal to U equal to kb t square derivative of d by dt, derivative with respect to temperature of log of root 2 pi kb t by mu. So this can be written as U is equal to kb t square d by dt of log this thing. You can remove the root and write the power as 1 by 2 raised to 1 by 2. So log a raised to x is equal to x log a, and you can use the property in here, so that kb into t square into d by dt of, here 1 by 2 will come here, log, let's write this like 2 by kb 2 pi kb mu times t. Clear? So the energy associated with a degree of freedom per molecule U is equal to kb t square. This 1 by 2 you can take out, 1 by 2 into log x. Let's say this as x and this as y. So log x into log y is log xy equal to log x plus log y. So d by dt of log 2 pi kb by mu plus log t. So this is equal to U is equal to kb t square divided by 2. Now let's take the derivative. Derivative of this one is a constant. So derivative of that equal to 0 plus now d by dt of log t. U is equal to kb t square divided by 2 into, you know, the derivative of log t is 1 by t. Now you can cancel this t and this t. So the final expression will be half kb t. So this is the energy associated with each degrees of freedom per molecule. Clear? So let's say for a monoatomic molecule, there are three. For a monoatomic molecule like argon gas, it has 3 degrees of freedom. So the total energy, E total, will be, you know, E energy associated with the degrees of freedom in x direction plus energy associated with y plus energy associated with z. But you know, each free degrees of freedom is associated with the energy half kbt plus half kbt plus half kbt, which will give 3 by 2 kbt. That is the total energy. Clear? So this partition, every energy is parted equally, and this law is called the law of equipartition of energy, because every degrees of freedom has equal energy. Let U bar represents the average internal energy associated with degrees of freedom per molecule. Let's represent that as U bar. That is the average internal energy associated with degrees of freedom, which means all degrees of freedom per molecule. That is U bar will be F into, F is the degrees of freedom into, energy associated with each degrees of freedom. We derive that as half kb into T. So, let's take for monoatomic gas. Monoatomic gas. For monoatomic gas, it has 3 degrees of freedom. So, U bar will be 3 into 1 by 2 kBT, or let's say 3 by 2 kb into T. Now let's represent U as the internal energy associated with a mole of gas. So average internal energy associated with a mole, let's represent that as U. And U will be U bar into Avogadro number. Clear? Because this is for a molecule. So in order to get a mole, you have to multiply that with Avogadro number. So U will be the average internal energy associated with a mole of monoatomic gas will be U bar, 3 by 2 kBT into Na. Or this can be, kb into Na is universal gas constant. Boltzmann's constant into Avogadro number is universal gas constant. So 3 by 2 RT. So that's our U. So you have molar specific heat capacity at constant volume is the derivative of internal energy with respect to temperature. Clear? So d by dt of, but for monoatomic gas U is equal to 3 by 2 RT, which is equal to, you can take this 3 by 2 R out, and dt by dt. So its value will be 3 by 2 R. So Cv equal to, always remember U bar represents the internal energy per molecule and U represents the average internal energy for a mole. Okay, I'm just erasing this. So Cv for monoatomic gas is equal to 3 by 2 R. Now from Mayer's relation you have Cp minus Cv equal to R. This is called Mayer's relation. And from this equation you can find the value of Cp. So Cp equal to R plus Cv, which is equal to R plus Cv equal to 3R by 2 or 3 by 2R. You can take this 2 to the left. So 2R plus 3R by 2, which is equal to 5R by 2. Now the specific heat ratio of monoatomic gas, let's say specific heat ratio or gamma monoatomic gas, gamma mono is equal to Cp by Cv. But you have Cp equal to 5 by 2R divided by Cv equal to 3 by 2R. Cancel. This 2 and this 2 are also get cancelled. So its value will be 5 by 3. Or its value is equal to 1.67. So this is the specific heat ratio of monoatomic gas. Clear? Now let's find out the specific heat ratio of diatomic gas. For diatomic gas like oxygen, nitrogen, etc., we have degrees of freedom. F is equal to, it has 5 degrees of freedom, which means 3 translation plus 2 rotation. I'm not talking about the degrees of freedom in this session. Anyway, diatomic gas has 5 degrees of freedom. Clear? So U bar U bar is equal to, F into half kBT, like we said before. So which is equal to 5 by 2 kBT. Clear. Now U is equal to, you have to multiply that is U bar times Avogadro number. So 5 by 2 kBT into Na, Avogadro number. So this is equal to this kb times Na is R. So 5 by 2 RT. Now Cv is equal to derivative of internal energy with respect to temperature. So d by dt of 5 by 2 RT, and its value will be 5 by 2 R. Now Cp is equal to, applying Mayer's relation, Cv plus R, that is equal to 5 by 2 R plus R, which is equal to 5R plus 2R divided by 7. So by 2, which is equal to 7R by 2. So gamma, specific heat ratio, gamma of diatomic molecules, as in the case of monoatomic molecule, it is Cp by Cv. But here Cp is equal to 7R by 2 divided by 5R by 2, which is equal to 7 by 5, or equal to 1.4. Clear? This is for rigid diatomic molecules. Okay, rigid. For non-rigid diatomic molecules, let's take that case also. For non-rigid diatomic molecules, we have degrees of freedom equal to 7. Therefore, we have U bar is equal to F into half kb into T, which is equal to 7 by 2 kBT. And U is equal to U bar into Na, that is equal to 7 by 2 kBT into Avogadro number, that is equal to 7 by 2 RT. And Cv equal to d by dt of U, here it is 7 by 2 RT, that is equal to 7 by 2 R. And from Mayer's relation, Cp equal to Cv plus R, that is equal to 7 by 2R plus R, 7R plus 2R divided by 2 equal to 9R by 2. So gamma diatomic for non-rigid, okay. Previous case is for rigid, equal to Cp by Cv, which is equal to 9R by 2 by 7R by 2 equal to 9 by 7. Its approximate value will be 1.28. Clear? So that's the specific heat ratio for diatomic molecules of non-rigid type. So these are just the application of law of equipartition of energy. We can find the specific heat ratio of different gases.